Hey folks, welcome to the next episode on Clear My Paper. Today, let's jump into a couple of interesting topics, but super important to culminate the understanding of matrices and determinants, and also very, very important from an exam standpoint of view. You ought to get some problems on this one. So let's stay focused and let's enjoy this episode. So we're going to talk about two concepts: adjoint of a matrix and inverse of a matrix. And pretty much this will be kind of derived. I don't want to define it first and then explain. I will keep on explaining and automatically will end up into the definition of this. We'll kind of naturally get traverse towards the definition as opposed to defining it first and then explaining. That's no fun. And as a quick recap, if you check out my last few videos, we would have discussed elaborately about two other concepts, which is minor of an element of a matrix and also cofactors. And as a recap, if you remember, whenever we are trying to determine or compute a determinant of a 3 by 3 matrix, what we do is we take each element and try to determine the minor or the submatrix of that and multiply by that. That's what we do. So in that process, whatever a submatrix is formed or the minor matrix is formed for an element, which means that we are going to eliminate that row and column where the element is present. For example, if you're talking about minor of A, we are going to cross out this 2 and we're going to get the determinant. So we have done a detailed video on this one. So just check out that one and you'll get more kind of understanding. But coming back to this video, so when we get all the submatrices in this format, if you see, these are all submatrices of different elements of this. So we have 9 elements in this matrix and we have 9 kind of submatrices or minor matrices. So each of these minor matrices, when you take the determinant of that, that's called as the minor of that particular element which was eliminated to start with. So all these submatrices or all these subdeterminants matrices are basically minor of an element. And the same thing that I've expressed it here on the right hand side, if you are more used to that row and column numbering, where this is the row 1, row 2 and row 3, and this is column 1, 2 and 3, and these are the elements suffixed with the row and the column tags, and this is how it will come. For example, there are nine elements over here and we have got 9 kind of minors here on this one. So those are the minors of matrix. And what is the cofactor is, we also kind of studied, or we also kind of understood where this notion of alternative sign comes, where all the diagonal elements are positive and all the non-diagonal elements are negative. In other words, you can say that every element alternates between the positive and negative sign, if you see here also, right? We got that also, and we understood how that comes from. And that's nothing but as a cofactor. So this whole matrix is nothing but a cofactor matrix where we have the minors in the determinant format for each element, and we also have the alternating plus or minus sign, and that's what completes the definition of a cofactor. So that's for the quick recap. So let's try to build on this furthermore for understanding the adjoint and inverse of a matrix. Okay, so I'm going to take the good old friend or set of equations that we had all along these videos. So we have these 3 equations that you have seen in the previous videos, where we have expressed each one of them as a linear equation with 3 variables, and we have kind of a coefficient matrix A, which is in this case this part with just the coefficients over here. So we also have that. And we also beautifully, what we have done is when we are trying to find the values of x2 and x3, or x1, x2 and x3, we kind of stumbled, or we derived the formulas by solving this as a set of simultaneous equations, and we came across 3 sets of equation x1, x2 and x3. And what we have done in essence is, whatever was given to us, and this is where you need to pay attention, right? Whatever was given to us, we were given 3 equations with 3 unknowns, x1, x2 and x3, and those were expressed in terms of y1. In other words, we had y1, or the variable, the y variables expressed in terms of x1, x2 and x3, where y is on the right hand side. So we were given the values of y1, y2, y3 in terms of x1, x2 and x3. And when we try to solve this problem to find the values of x1, x2 and x3, what we kind of end up doing is we flip it around. So we start expressing the values of x in terms of the y. If you see, the terms on the other side of the equal sign has changed. Over here it's y1, y2, y3. Over here it's x1, x2 and x3. So this is called as inverting the whole equation, which also means that solving the whole equation, which also means finding the value of x1, x2 and x3. It's all mean the same. So what we're trying to say, values of x1, x2, x3 below are expressed in terms of y1, y2, y3. That's called as inverting the equation, where right hand side and the left hand side are inverted as opposed to the given equations. That's number one. And we also kind of studied that regardless of how this x1, x2, x3 look like in terms of the denominator, which is a determinant, the variables might look different in terms of how they arranged and how they are computed. But determinant of the whole matrix, all these denominators on the x1, x2 or even on the x3 are nothing but determinant of this coefficient matrix D, right? The value of that will be always the same regardless of however you compute. That's the beauty of the determinant. So although all these denominators for x1, x2, x3 look different, the value will always be the same, and for the solution to exist it will not be equal to 0, and we have done that zillion times. Okay, and this is what will help us in defining the adjoint and the inverse of the matrix. And if you also remember a couple of episodes before, I told that all this while we are going to focus on the denominator, or we have been focusing on the denominator, but in this video or in this episode we'll be focusing on the numerator part of each of these equations. And at the outset you can easily see there's a beautiful symmetry which I also discussed earlier between the numerator and denominator. So except for the coefficients over here, if you see the items in the within the braces for denominator, it's the same for each of the variable, right? For the numerator and denominator are same for x1. Similarly, if you see the items or pretty much this kind of a sub-matrix over here, or the minor, right? It's the same for the numerator and denominator for the x2, and so far with the x3 also it's the same. So that's a symmetry that we're going to unpack today, which we also saw that how it beautifully unpacked leading into Cramer's rule, and in this episode we'll see how it beautifully unpacks in defining adjoint and inverse of a matrix. So remember that we are focusing on the numerator for now. So by that what I mean is, let's try to simplify this equation. So we have got three equations, x1, x2 and x3, and we're focusing on the numerator part of that. So let's focus on the numerator. So what we can do is, this whole equation we can always express in terms of matrix notation. Like we know that we know how to express this into matrix notation, but now we have inverted, meaning that we have found x1 in terms of x in terms of y variables, and we have got three equations, and the unknowns have gone on the left hand side. So we can express these three equations in matrix format, which is kind of this part here. So I'm taking the x1, x2, x3 in the matrix format, and so since the determinant for all the three variables are the same in terms of value, I'm just calling it as d, and it's in the denominator, so I'm saying 1 by d. So instead of expressing this separately in terms of variables, I'm just interested in the value, and since the answer or the value is the same for all the denominators, and I'm just taking it as one time without repeating it, because we want to express the whole equation in the matrix notation, a compact format. So I'm expressing that, and multiplied by what I'm doing over here is I'm simply taking the numerator for all the three equations, focusing on the numerator only. Okay, this is the numerator. I'm focusing on the numerator, and I'm just writing the coefficients of the variables y1, y2, y3, just how we wrote the coefficients here. In this case, if you see, we just wrote the coefficients of x1, x2, x3. So there is no x1, x2, x3 within the matrix. Similarly, we are going to remove the y1, y2, y3, and we're just going to write a coefficient matrix of the numerator for each of this equation, x1, x2, x3, and which is what we get here. If you see the x3 numerator here, we have got dh minus eg. I'm going to get dh minus eg as a third row. Then we have minus ah minus bg, and we have got as minus bg, and then we have got plus ae minus bd. So what I've done in essence here is all the numerators coming together as coefficient. I've written that because that's what matrix notation is all about, expressing that in compact format. So what I have on the left side, this is the left hand side. So I have left hand side is equal to, which is the value of all the three unknown variables in x, is equal to 1 over the common determinant of the common matrix, which is this one, A, B, C, D, E, F, G, which is the denominator for each one of them. So this piece is the denominator, common denominator, or the value is the same. And then I have got all the numerator for all the three equations expressed as in terms of coefficients. And this is where the symmetry and the beauty of symmetry kind of starts coming out, which I've kind of put in a red box. I have not filled this yet, but I want to explain this and then figure out what's going on. So far, hope you guys are with me. So now just focus on this portion, this matrix that we have, right? The beautiful new matrix, which are coefficients of the y variables in the numerator for all the three equations. And let's compare that with the cofactor matrix, which is what this matrix is all about, right? For the cofactor of the given matrix, whatever is given A, B, C, D, if we derive a cofactor of that, which is finding the minor of each element and alternating the plus or minus sign, that gives us the cofactor matrix. So I copied the same cofactor matrix at the bottom here for ease of convenience, and you just focus on this part, this matrix and this matrix, and you see what's going on. So if you see, all the diagonal elements are the same on the backslash diagonal, this one on the matrix. So this one, this piece and this piece is the same. If you see here, we have EI minus FH, and if you solve this, it's going to be EI minus FH, then AI minus CG, then you have got AI minus CG, and then AE minus BT. So the diagonal elements starting from the top left to the bottom right are the same. And just focus on the elements on the remaining side. So let's take this particular element here. It says minus BI and CH. So it's in row 1 and column 2 here. But if you see this same element in the cofactor matrix, it's coming over here in row 2 and column 1. Whereas if you multiply this BI minus CH, and there's a negative sign on the outside. So we have a negative sign on the outside. And then if you find the determinant of this 2 by 2 minor matrix, it's BI minus CH, which is what we get here. And similarly, if you go to this is appearing on the first row and third column, but this whole thing in the original cofactor matrix is appearing in first row and first column and third row. That's what it's coming. So that's what is happening. So what's happening is, looks like all the elements are reflected or interchanged across the diagonal, which means the rows becomes columns and the columns becomes rows in this, between this and this. So let me repeat it again. So when we find the inverse of a matrix, and while we're finding that, so whatever happens on the right hand side when we form a coefficient matrix, if you compare that with the cofactor of the original matrix before the inversion over here, this part, if you compare with the cofactor of that matrix, the rows and columns of both the matrices are nothing but transpose of each other, where the rows and columns are interchanged. And that's a beautiful symmetry here. So what I can write in this red box, which is a fill in the blanks, is the inverse of a matrix, meaning the values of x variables x1, x2, x3 can be expressed as 1 over the common denominator, which is a determinant, multiplied by transpose of cofactor of the original matrix A. That's what it is, right? That's how I can write. And this particular transpose of a cofactor of the original matrix is nothing but the adjoint of a matrix. So whenever you get an adjoint of the matrix, what you need to remember is it's nothing but transpose of a cofactor of the original matrix, and the cofactor itself is nothing but a matrix of different minors with alternating plus or minus signs. That's what it is. So it looks kind of going back and forth, but if you just clarify each term and talk it out slowly in your head, it makes very good sense, and you can appreciate how beautiful the matrix is, how many things are, how much intelligence is unpacked in a simple matrix notation, where you can get different problem solving skills very easily. So what did we done in this kind of episode, right? Inverse of a matrix A, inverse of any given matrix A, which is, let's say this is the matrix A, is nothing but 1 over the determinant multiplied by transpose of the cofactor of the matrix A. Whatever is the given matrix, if you find the cofactor of that, which is this is the cofactor, and if you transpose this in terms of rows and columns, which is what you get this, that gives us the inverse of the matrix. In other words, this transpose is called as adjoint. So I can also say that inverse of a matrix is equal to 1 over the determinant multiplied by adjoint of the matrix A, which is the compact form. And in terms of notation, this is how it's expressed. When I say A superscript -1, so that means if it's a regular matrix is A to the power, it's not a power, but it's in the power position. A superscript -1 is nothing but inverse of this matrix equal to 1 over determinant, and in the bracket we say adjoint of A, which is adjoint of the matrix, which is nothing but transpose of the cofactor of matrix A. So that's what is all about adjoint and matrix. I wanted to take some time and put this video separate so that people don't get confused and what is it. And I hope you understood the beauty within the algebra, how things kind of start unpacking and leads one thing to another thing. And it's all based on the same set of old school solving simultaneous equations, which we kind of did in previous episodes. And the same thing we are carrying forward to explain one concept, and all the concepts, whether it's a transpose, it's a adjoint, it's a minor, it's a cofactor, all are interleaved and all have connections with each other, and those are the connections we need to understand to explore the power of matrix. Hopefully you enjoyed this video, and if you want to know more about the geometric side of that, what exactly inverse means as an extra reading and as an extra intuition, I'll be putting a video on that, so watch out for that and we can enjoy that as well. Otherwise, it's a wrap up on this episode on adjoint and inverse. Stay tuned on Clear My Paper, more videos coming up for your reference. Thank you.